Greetings, students. In this tutorial, we're isolating one small but critical piece of the discrete Fourier transform algorithm, the Twiddle factor, written W subscript n superscript kn. If you've worked through the DFT, you've already seen this symbol sitting inside every butterfly diagram. But most students can manipulate it algebraically without actually being able to evaluate it by hand for a given k, n, and n. That's the gap we're closing in the next few minutes. By the end of this segment, you should be able to take any w sub n to the kn, reduce it to a single complex number in rectangular form, a plus jb, without a calculator, using nothing more than the unit circle and Euler's identity. Formally, a Twiddle factor is a complex-valued trigonometric constant, defined as w sub n up kn equals e to the minus j 2 pi kn over capital N. The subscript n tells you the DFT length you're working in, how many points you're transforming. The exponent kn is the product of two indices, k, the frequency domain index, and n, the time domain index. Notice this is purely a function of the ratio kn/n. It does not depend on your actual signal values at all. That's the key conceptual point. The Twiddle factor is a property of the transform size and the specific k, n pair, not of the data. Why does this matter for FFT complexity? In a direct DFT, you'd compute n output points, each requiring n complex multiplications. That's the O n squared cost. The FFT's divide and conquer structure breaks the transform into smaller subtransforms, and the Twiddle factors are exactly the correction terms, the phase rotations, needed to recombine those subtransform outputs correctly. Because there are only n distinct Twiddle factor values for a given n, and they can be precomputed and reused across every butterfly stage, the recombination cost collapses to O n log n. So this innocuous-looking exponential is the entire reason the FFT is fast. Now, how do we actually get a number out of e to the minus j theta? This is where Euler's identity earns its keep. E to the minus j theta equals cosine theta minus j sine theta. This converts an exponential with an imaginary argument into a rectangular complex number, a real part from cosine, an imaginary part from negative sine. Every Twiddle factor evaluation you ever do will follow this exact substitution. Let's use an example to delve deeper into these concepts. Let's evaluate w sub 4 with k equals 1 and n equals 3. Step 1. Substitute directly into the definition. Multiply out the exponent. 2 pi times 3 is 6 pi, divided by 4 gives us minus j 6 pi/4, which reduces to minus j 3 pi/2. Always reduce the fraction before going further. It makes the angle easier to place on the unit circle. Step 2. Apply Euler's identity. E to the minus j 3 pi/2 becomes cosine 3 pi/2 minus j sine 3 pi/2. Step 3. Evaluate the trig values. 3 pi/2 radians is 270 degrees, 3/4 of the way around the unit circle. At that angle, cosine is 0 and sine is -1. Substituting, 0 minus j times -1, which simplifies to plus j. So w sub 4 up 1, 3, equals j, a purely imaginary number sitting at the top of the unit circle. Notice the pattern of the workflow. Substitute, reduce the angle, apply Euler, read cosine, and sine off the unit circle, simplify. That 5-step sequence is identical for every Twiddle factor you'll ever evaluate. Only the numbers change. This time, try it out. It's your turn. Same n equals 4, same k equals 1, but now n equals 2. Work through the 5 steps at your seat. Substitute into the exponent, reduce the fraction, apply Euler's identity, read the unit circle values, simplify. Check if you can answer this in just 30 seconds. In the end, you should arrive at the answer as seen on the lower right of the presentation. Were you able to get the correct answer? Let's have one more example. If you can do it faster, that's better. This time, we have capital N equals 4, k equals 1, n equals 1. Same 5 steps go. Same thing. You should arrive with the answer as shown. Try it out evaluating with different values of capital N, k, and n. If you have questions, just message me and I'll get back to you. Good luck!